Bueno, ¿podemos empezar? ¿Empezamos? Let's start. Bueno, esta es la conferencia de cierre. Acá Néstor no quiso cerrar, me mandó a mí al frente. Más o menos hace un año, cuando empezamos a organizar este encuentro, teníamos muy en claro a quién queríamos invitar de manera especial, y ese alguien al que queríamos invitar de manera especial es Pasachoff. Yo creo que no hay nadie aquí, o por ahí hay alguien, pero se está enterando ahora, que no lo conozca. Para mi generación, yo soy una persona que tiene muchos años, y tengo varios compañeros, la verdad que está lindo estar acá. Néstor fue compañero mío de la facultad, el Vasco fue compañero mío de la facultad, es decir, estamos como volviendo un poco atrás. Creo que hubiéramos dado, no sé, 10 años de nuestra vida por tener una copia de la guía de estrellas, de la guía de campo de Menzel y Pasachoff, y obvio que quién podía tener eso, excepto la biblioteca de la Facultad de Ciencias Astronómicas y Geofísicas de La Plata, y nos peleábamos medio por la guía de campo para poder observar, por lo menos aquellos que teníamos una marcada inclinación a la astronomía casi aficionada. Estábamos haciendo la carrera y nadie nos llevaba a observar nunca en ninguna parte, y lo hacíamos de motu propio. Pero además, lo interesante, ¿por qué invitarlo a Pasachoff? Porque creo que debe ser la persona que más eclipses ha visto en su vida. How many eclipses did you see in your life? How many?
64.
¿Cuánto? 64. 64 eclipses. Fue protagonista de 64. Sí, de sol. 64 eclipses de sol, no está contando los de luna, obviamente. De manera que es una persona que ha hecho no solo trabajo vinculado con la difusión y la enseñanza de la astronomía utilizando eclipses y ocultaciones, sino trabajo profesional. De manera que para nosotros es un placer, ya ven, no lo dejamos que se presente solo, se presenta solo, pero es un placer que esté aquí la persona que probablemente es un referente en el mundo entero, no probablemente, es un referente en el mundo entero en lo que hace a los eclipses, y que creo ha participado en los últimos años de todos los eclipses, de manera que for us it's a real pleasure to have you here. Jay va a hablar en, bueno, creo que va a decir, if you say in Spanish your words, your first.
En español, he estudiado el español en la escuela en Nueva York, pero es solamente mi segundo día en Argentina, este visita. Entonces es necesario hablar la conferencia en inglés.
Very good. Excellent. Así que va a dar la conferencia en inglés, de la misma manera que hemos escuchado a nuestros amigos de otros países. Así que lo va a hacer lentamente, y después las preguntas las traduciremos. Muchas gracias. Thank you very much, Jay, to be here.
Gracias, para usted. El segundo por Néstor. And here is an eclipse of the sun with the moon and the sun and Jupiter. How many of you have seen a total eclipse? Excellent. And how many have seen an annular eclipse? Okay. So I am looking forward to seeing an annular eclipse with you on Sunday morning, and everything looks very favorable. So let us hope that it works. The sun and the moon, of course, are much smaller in the sky in real life than the close-up pictures that we see in lectures or in books. So mainly we work with close-up images. The European Space Agency has had a satellite, Solar and Heliospheric Observatory, for 20 years that looks at low resolution at the outer corona, and we have this whole portion of the sky to study at solar eclipses that cannot be observed from space. Space can observe with filters in the ultraviolet in the middle to get very hot gas, million-degree gas, and it can block out so much of the bright corona, but the corona is 1,000 times brighter here than here. And we just can't do that in a single frame in a camera. There's too much scattering around. So all this is blocked by this, what's called C2, the second of the coronagraphs on SOHO. And we fill in on the days of total eclipses about every 18 months what the shape of the corona is like. And you can see these beautiful structures that are held in place by the sun's magnetic field. So we are studying the sun's magnetic field. And every time we look, it is different because we're at a different phase of the sunspot cycle with a different magnetic field. So often we fill in with some single photographs, and this is the difference between a single photograph and the composite of a few dozen photographs that you just saw. But here you can see how much brighter it is here than here. And so one of the nice things is that whenever you take a picture of a total eclipse, the exposure is not that important because every picture is good. You just see more corona or less corona. And here in the middle, a photograph has been, an image has been taken from space, and I'll come back to that, and paste it on the size of the moon so we can trace back the features that we see in the outer corona. Now this is solar minimum of the sunspot cycle. You can see very few streamers, and they're just at the equator, and this is what we expect to have this year.
Microphone down, you might go off.
Does somebody want to play with this board?
Hola, hola, hola.
What happened?
I don't know.
Battery. Hello? Does this one work here? Yes. Okay. Sorry. Thank you. Anyway, as many of you may know, there was a demonstration near the obelisk in Buenos Aires yesterday, and we got to the airport with my colleagues just minutes too late to get on the flight yesterday. Some of you may not know that today we were on about to board the flight when the pilots caused a strike in Buenos Aires, but here I am. But anyway, so I had the opportunity to go to Malva in Buenos Aires yesterday afternoon, where I wanted to see this painting that I hadn't seen before. And so it is Diego Garcia here, Dr. De La Serna, and I noticed a few years ago that in his eye there is a total eclipse. And we have traced what Rivera saw, Diego Rivera and Frida Kahlo saw. We actually have a picture of them watching an eclipse of the sun from the United States some years after this was painted. But there's no doubt that it is an eclipse that was painted in 1915. So I recommend that to you next time you're in Buenos Aires if you haven't seen that already. And then the tower just opposite the train station has all these wonderful suns on it, and of course the beautiful sun of May and the Argentinian flag. So it's very nice for me as a solar astronomer to come to Argentina and celebrate the sun. I wanted to start talking about these eclipses with an annular eclipse that crossed the United States in 2012. It actually started in Asia and came on the Pacific Ocean, and the end was in the United States. So low in the sky, we could see the annularity, and of course, just as the annularity came, a cloud came and broke some of that. You can barely see the annular eclipse here. So of course, only a couple of percent of the outer layer of the solar photosphere was visible then, but it made a very nice effect. We were at the Very Large Array, which is this tremendous set of radio telescopes in New Mexico. Many of you have met my colleague Rob Lucas, who was sitting in the middle. there who helped us with the students and observed at that time. And you'll see both of us wearing our orange pants at the Eclipse on Sunday, so you can pick us out. I guess he started matching me only after this 2012 Eclipse. But here are students from my solar physics seminar, and again, I'm giving a solar physics seminar at Williams College this spring, and we hope to have a lot of our students with us at the Eclipse. Here's just an artistic view, a round view with the antennas there, and the beautiful annular eclipse that we got there in 2012. And of course, these are all with filters on. So we work with several of the filter manufacturers, especially for the professional work, Thousand Oaks Optical, for getting the right exposure and the right filtration there. And my colleagues, Rob Lucas and Bryce Babcock, are people I've been working with at Eclipses for a long time. Is this now working again? Good, thank you. So here again is a series. The moon gradually came over the sun for an hour and a half or so, and then we just had a little cloud right at annularity. And then the science we were doing was watching the moon cover the active regions on the sun, and even though the Very Large Array has very high precision for mapping anything, including mapping the sun, since we know exactly how fast the moon is moving, we know exactly how fast the moon is covering a sunspot region, an active region on the sun. We're trying to pinpoint just where the heating of the solar corona is, to millions of degrees. And there are X-ray observations at high resolution also, and we can compare them better with this kind of mapping. So we hope to do that again this year. And then the VLA couldn't point below that angle, so in fact we were no longer using the VLA as we watched the sun set. I want to spend a little time with the following eclipses. After that one, there was an annular solar eclipse that came across Australia right after a total eclipse that came in part of Australia and out to the Pacific Ocean. So I'm going to talk about that first, and then about the eclipse in Africa in 2013, and then about the eclipse in the Arctic in 2015. So in late 2012, the eclipse was started low in the sky in Australia. I like to make my scientific observations from dry land and not on the rocking of a ship or of an airplane. So we went as far east as possible while still on dry land for this eclipse. Though we then compare results, I'll show you in a minute, with someone who was on a ship north of New Zealand there. And you see it didn't quite reach South America on that occasion. As it turns out, the weather was spotty. It was clear some places, cloudy some places. And I had to fly above the clouds in a helicopter to see totality, but you can see the shadow of the moon come in very nicely there and surrounding the corona in the sky. And we have a lot of people who travel with us now, some of our alumni from Williams College, some of my current students at that time. Here's Rob Lucas and Helen Robinson, who you've seen here, who've been with me for a lot of eclipses. So, in fact, at the last minute, I took off in the helicopter. Fortunately, there were some holes in the clouds because you're not allowed to go through completely dense clouds, but we could follow up on the hole. You can see some sunlight coming through the hole to the ocean. And then I like to use these chromium filters. In fact, I have brought some for a film crew that is with me. We're going to make a film for the public television show Nova in the United States in July, in August, and they're getting it already. So in any case, we like to use these glass-covered filters, and you can see the partial eclipse through the filter, which is letting only one part in 100,000 through, and you can see that if I expose that better there, then the sky is entirely wiped out, even with the dense filter. But at least it's safe for the eye and safe for the cameras, and we can very well watch the shadow come in and envelop us at the eclipse. This beautiful image. But the night before, we had forecasts that on the other side of a mountain range, it would be clearer for the eclipse. So some of my people took telescopes and CCD detectors and went inland, and led by Ron Dantowitz and Bryce Babcock. We got with the Takahashi here, we got these beautiful views showing the prominence on the edges of the sun here, and some Bailey's beads that lead to the diamond ring effect, which I presume has been discussed earlier in this seminar. There were some nice prominences on the limb, and of course these get covered over within seconds. And then eventually, the chromosphere begins to appear on the other side with a diamond ring on the other side, and totality is over. In the meantime, longer and longer exposures show the shape of the coronal streamers. Again, they're held in place by the sun's magnetic field. And here you can see that there were streamers at all latitudes going off in all directions, like a porcupine. So this is closer to solar maximum. I see you've made it back here. So we also work with taking spectra. My colleague Ron Dantowitz has one spectrograph. My colleague Aris Voulgaris from Greece has another. And so here is the spectrum of the sun spread out there. And in 1868, Jules Janssen in India noticed that instead of just the bright lines from sodium that he expected, there was an even brighter line nearby that was unexpected, and they didn't know what to make of it. And after some work and some work in England by Norman Lockyer, they named it helium after the sun god, because it came only on the sun. And of course, you know that helium is one of the basic chemical elements, but they didn't know that then. So this is an example of something we discovered at an eclipse that it then took decades for other people to follow up on. And then you can see some faint line here in the green, and even fainter one in the red, and those were discovered a couple of years later, and they called them as though they were coming from coronium, because they existed only in the corona. But you also all know that there is no coronium element in the periodic table. The periodic table was getting filled in, and that turned out, although it took 70 years to find out, that turns out to be a sign that the corona is millions of degrees hot. This green line is from iron that has been heated, and if you heat it a bit, it loses an electron. You heat it more, it loses 2 electrons. To lose half of its 26 electrons, it has to be heated to millions of degrees. So this green line is from iron that has lost half of its 26 electrons, and the red line from iron that has lost 9 electrons. And when we're at solar maximum, which you just saw, the corona is hotter, and the green line is stronger than the red line. And at solar minimum, it's the other way around, and the red line is stronger than the green line because the corona is cooler. And that's one of the things we are monitoring at these eclipses. And these are just enlargements of what we had up above. For example, the helium line there, and this red line of iron, 9 times ionized, and this green line from 13 times ionized iron, and the helium line. So here is a composite with some of our imaging here, and the solar maximum corona from the C2 coronagraph made by the U.S. Naval Research Laboratory, which is on the European spacecraft. And you can see how these things line up. And then we have the ultraviolet picture in the middle, and at least for the half that is on the side of the sun that is facing us, we can see some eruption begin here and trace it up through the eclipse and then into space with the spacecraft. Now, I mentioned that a colleague was on the ship north of New Zealand, And it turns out it took 39 minutes for the for the eclipse to reach New Zealand from Australia. And in that time, a coronal mass ejection had erupted and was moving out in space. And the arrow tip was 635 kilometers in under an hour, so it was above the edge. So literally that is going more than 1 million kilometers an hour. So there are these tremendous eruptions. The ones that go off to the side like this aren't going to hit us on Earth, but sometimes you see them as a halo around the sun, and then they're coming right at us. And then we have to beware. And now that we are so dependent on our electronics and our satellites, we really want to be able to predict these things, even minutes, not to mention hours, in advance. So here you can see from Australia, and then just 39 minutes later, 36 minutes later, 37 minutes later, you can see this big eruption come out. Yes, thank you very much. In this 2012 total eclipse, also my colleagues Zora Mikic and John Linker have made this prediction based on the sunspots that they see and that the spacecraft and the ground-based observatories are measuring, and they can make predictions as to what the magnetic field will be at higher levels. And you can see it matches pretty well, but not with the same detail that we can actually see at an eclipse. So that's one of our projects for this forthcoming eclipse. We're working with them again. They're going to make predictions, and we're trying to improve their predictions by comparing the predictions with what we actually observe. Here you can see the side-by-side comparison. And then another colleague, Yimlin Wang from the Naval Research Laboratory, also uses the magnetic field. He uses a different method to make his predictions, and again we try to line up his predictions with the streamers that we actually see and measure at the eclipse. Now NASA has a series of spacecraft to study the sun. Of course, the sun is so bright that you can't point the big famous nighttime spacecraft at it. Hubble telescope can't point at the sun. Although my colleague Len Schneider says he once had an observation through the back of the mirror with the telescope pointing away, and there was some residual. But in any case, here's from the Solar Dynamics Observatory the magnetic field, and you see, well, strong magnetic field. There are 3 big sunspot groups here, at least 2 here in the magnetic field. And if you look with one of those ultraviolet filters showing the 1,000,000-degree gas, you can see, first of all, how the hottest regions do correspond with the magnetic field. So this is magnetic heating that is going on. And you can see what the sun looks like at a maximum of the sunspot cycle. And then there are half a dozen different filters. This one shows 50,000-degree gas, cooler gas, from helium, actually. But you can see it's the same active regions here, and then we just go up and up and get hotter and hotter gas as the energy is funneled up. And one of my sets of experiments for this eclipse coming in August, with the help of the National Geographic Society and the National Science Foundation, is to make some very fast measurements to try to see vibrations that are going on in these various loops to see if that matches one or the other of the predictions about what's happening. My student, Dan Seaton, former student, has actually been able to see the eruption occur on the disk of the sun and then follow it out into space with a spacecraft run by the European Southern Observatory out of Belgium, and there's a new spacecraft, a successor to that was just launched by the weather satellite people of the United States that I'll show you a picture of later on. But from the SOHO spacecraft, you can actually see the eruption here go on, but you see it's kind of fuzzy, and then it's even fuzzier here. Well, the pixels we get at the eclipse are more than 10 times better, smaller than the pixels we see in this spacecraft that was, after all, launched 20 years ago and designed 5 or 10 years before that. So there's an overlap region in which we can do much better. And here's a composite image we have from that 2012 eclipse. And again, the solar maximum configuration is overall very round because of all the streamers at high latitudes. And Mr. Lundorf, 100 years ago, started plotting the flattening where this is elliptical, a pretty squashed circle, and this is pretty round. And you can see we're down and very round in 2012, but 3 years before that, for the eclipse in China in 2009, there were only a few streamers, and it was very elliptical. So we follow the flattening index over time. And so here is a processed image here embedded in the spacecraft image. And we publish our results very regularly in the Astrophysical Journal, sometimes in the journal Solar Physics. And so we're working on spreading our scientific results through the astronomical community. So that was the eclipse here. Here. And then there was an annular eclipse that came through the middle of Australia before it went out to sea, and then we'll go to the eclipse. Well, this one you saw in the United States, and then we'll go to the eclipse in Africa. And so in May 10th, 2013, a few months later, after that Australia total eclipse, the sun rose in some heavy clouds, but we could see it, and then it cleared up by the time we had annularity really out in the outback of Australia. And you can see that the day began to heat up. It was 25 degrees Celsius and would have kept heating up through the day except an eclipse started. And so we see a deficit of, say, from 30 to 24 degrees or so, a 6 degrees Celsius deficit because of the eclipse cooling. So participating with some people who are measuring the effect of the eclipse on the Earth's atmosphere. I am most interested personally in the total eclipses. This one began over the Atlantic and the partial phases didn't quite reach Argentina, and we wanted to be on dry land again, so we got it soon after it hit the coast of Africa in Gabon. And you can see that the partial phases reached all the way up to Spain and down to most of South Africa, but just the northern part of South America there. And as we do our work, sometimes we have to really watch out for encumbrances. In particular, in the African eclipse, we had to watch out for elephants. And then the following eclipse, we had to watch out for polar bears. And then the following eclipse, we had to watch out for Komodo dragons. So there's a different circumstance at each time, and that's kind of fun. And for this eclipse on Sunday, I only had to watch out for Aerolíneas Argentinas pilots. But we were watching from the edge of the La Lope National Park in Gabon, and so we could not actually go right to the central line because of the elephants. This really affected where we were. And we went to a nearby village. We weren't too far off the central line, and we were treated very well in the village. People did a dance to welcome us. And we had with us one of my current undergraduates, an alumna who was doing some work in Gabon, Rob Lucas, and some other colleagues were with us on that occasion. And here we are with our Williams College banner here in Gabon. We were helped by the people in the Park Service, and there was a lot of time we spent in bureaucracy getting our equipment into the country. Here's another movie. Let's see if we can listen. Can it be any louder? Or maybe not. So just listen. There's the diamond ring, went away, so there's totality. And this is going to last a minute, and I'm part to show you this to show you how long a minute is when you're in totality. There's plenty of time to look around, take some pictures, walk around. Notice the sunset effect looking out of the umbra, but we're in the umbra here, and a close-up insect. Beatrice, can the lights be turned off on the other side of the room? Well, here we're getting the diamond ring. So you can see that a 1 minute eclipse is ample. And really I like to say that the most exciting part to be outside of a total eclipse is the 2 diamond rings, and you need 125th of a second in between to take a photograph. And anything else is extra. Of course, we want to use more time for more observations, but basically you want to choose your location. And we see this in the United States this coming summer. We're choosing more for the statistics on the weather than we are with details of a few seconds, more or less, of totality. But there's such a difference here. 2 pictures, just a few seconds before totality. The sky's so bright you don't actually see the corona, and then just a few seconds later, here I am taking a picture of the sun in a darkened sky. And we had this beautiful shape of the corona with ejections going out. Here is what's called the coronal mass ejection. A bit of the corona is broken free and is coming out in space. And then one of these prominences on the edge of the sun, which is glowing the red of hydrogen radiation, H-alpha, has come out there too. And I'll show you another picture with another coronal mass ejection. Now, in 2013, things are still pretty round for this eclipse. We have a spectrum here, and we again have the green line stronger than the red line at this phase of the maximum sunspot cycle. We've put together, it was published in Astronomy Picture of the Day. How many of you ever look at Astronomy Picture of the Day? Just a few. It's quite a good site from NASA. You just go to APOD or Google APOD, Astronomy Picture of the Day, and you get something interesting every day. So anyway, it was nice to have this coronal image here with a sandwich between the spacecraft image and the image from space, and you can see the size and importance of that coronal mass ejection that went out, and this is turned now sideways, but you can see a second mass ejection was going out at the same time. So the sun was very active at that time. And my student Tina Seeger put together some observations from different sites across Africa. They're all with different angles and different exposures, but you can actually see the motions and measure directly in kilometers per second the amount of the motions. These are just from 2 sides of the national park. You can see this big bow shock come out, and then a little bit of a closer up here, you can actually see the head of this coronal mass ejection move in the time that the eclipse took to go across Africa. So here is a composite of our processed eclipse image with the spacecraft image. So you see how low the resolution is. It's a beautiful thing, and you can watch it go. And then we can paste in the spacecraft imaging, and we can make, as Wendy Carlos does working with me, an overall link of all the different images to see the complete picture of the sun on that day. And we can study the different features, the knots here, and measure all those velocities together, especially with my colleague Wojtek Rusin from Slovakia, and his colleague Meto Ceniga, and Alan Davis was my student then. And in fact, now he's a graduate student at Yale, and he gave my lecture at Williams College 2 days ago to allow me to leave to come here. But anyway, here we've pasted on our image from the ground of the eclipse, and you can see that there's just higher resolution here than they had in the spacecraft. Even though the spacecraft can actually see the eruption at low resolution, but get the overall motions. The new spacecraft Solar Dynamics Observatory can make some beautiful images here. And we can put that together with our imaging at the edge of the sun to see the details, and we're working on that. And then people can make simulations as to what the corona would look like. I I mentioned the ones by Yin and Wang, such as this one, but NASA has some spacecraft partway around the Earth's orbit to view from the sides too, so we can see the whole sun now and not just the face that is coming toward us. And so here's one of his calculations with an overlay of our eclipse imaging. Not every year has a total or an annular eclipse. Those are called central eclipses, when the moon goes over the center of the sun. But every few years there's a year with no central or annular eclipse. And in 2014 there were a couple of partial eclipses, never a central eclipse, and I was able to go to Albany, Western Australia, just to see the partial eclipse. It's okay to have some clouds when it's only a partial eclipse, but let's not do it for an annular, certainly not for a total eclipse. And that we actually watched from the same site that my wife and I went on our honeymoon many years before. And then from the Sacramento Peak Observatory in the United States, in October 23rd, 2014, we had a partial eclipse. And on the sun that day was the biggest sunspot group that we had had in decades. So it was really very, very striking. The sunspot number, which is not exactly the number of sunspots, it has to do with the grouping into groups of sunspots. Also, as you see, goes up and down, and we've just passed this peak, but you see it's a low peak, and only half the height of the previous peak, and maybe a third or so the height of the peak previous to that. So we are very bad, we solar astronomers are very bad at predicting the sunspot cycle. The sun has not revealed that mystery to us yet, and people are working hard to see what clues there are to what will happen in the next cycle. In 2015 there was an eclipse that went off the coast of Greenland, it missed Iceland, it hit the Faroe Islands, and then went up to this archipelago called Svalbard, which is run by Norway, and went up to the North Pole. So this is at latitude 78.5 degrees, the furthest north that I have been, and the shadow is very elongated because it was just draped over the curvature of the Earth at that time. And then we did have to watch out for polar bears. It turns out that if you go more than 2 kilometers out of the capital, Longyearbyen, you were obligated to have a rifle with you and to have rifle training in advance, or have a trained rifle person with you. And as you'll see in a minute, we did have to go out of town because the mountains were higher than the sun is at 78.5 degrees. It was only 10 degrees above the horizon, and the mountains went to 11 degrees above the horizon. So the reindeer were benign, but there was somebody mauled by a polar bear who had gone miles away where he shouldn't have been. But it was a very clear day, and we could see the prominences. My student Alison Carter took a lot of these images. We could see a prominence erupt here in H alpha, and the prominence is on the edge of the sun. And here's a composite image showing the structure, which is partway between maximum and round, but there are some deficits in portions of the sun. And Rob Lucas made this wonderful movie, and thank you, Rob. And you could see, I'm going to play that again because I like it so much, but you can see that the sun was lower than the mountains here, so we had to come out on the ice and be there for hours. I had only a little frostbite, and I did recover from that. So this is speeded up by a factor of about 10, and you can see the partial phases there, and there comes the shadow across, and totality. I'm going to play that one more time because it's just great. And the overexposure there with even the little bit of partial phases, but then totality and the umbra coming across. So that's what it's like to be out in an eclipse. And then somebody else there, Ak was making a movie, and again this time to scan around where we were. There was a glory in the sky of refraction in ice crystals of the remaining sunlight. And so here are the last, this is now in real time. And so going back to the totality of atom again, here's the umbra coming in from the side. There you can see the silhouette of the moon there. You can barely see Jupiter up there. You see how dark it got? So that's really fun to be outdoors during the eclipse. And I keep trying to convince 300 million Americans that they all want to be in the path of the eclipse and not off to the side. And instead of it saying somewhere 99% coverage, we're trying to get some maps that instead of 99% coverage, it says 10,000 times brighter than during totality. Instead of 90% coverage, it will say 100,000 times brighter than you want it to be. And we're trying to get across the difference between the total phases and the partial phases. So here's where we were set up in Svalbard. In the meantime, this European satellite went around over the Earth, and then it went halfway around the Earth, and it got another eclipse 45 minutes later. But you can see all the details we're seeing in these loops of gas in the magnetic field. And so we put together this map of a month of the rotation of the sun, so we could see what went into the formation of the configuration of the sun that we saw at the edge of the sun, the so-called limb, on the day of the eclipse. And then we could link our eclipse observations with the pictures taken from space to see the white light difference from the special filters for the very high temperature gas. And just a series of observations with different exposures just gives you an idea of how you get these images that are amalgamated, and you just take a lot of these images with all the different exposures and select the properly exposed pictures out of each of them to make a composite image like this one that shows the details of how the magnetic field holds the gas in place. Here is what the sunspot number was doing at the time. The yellow is the day-by-day variations, and there was the average. You can see that there was a double peak in the sunspot cycle. The northern and southern hemispheres peaked at different times, and that tells you something about how the magnetic field of the sun connects underneath the sun, though people are not sure exactly what it teaches you about that. And here's a composite again with the spacecraft view and our eclipse view, and the other spacecraft rotograph view, and the views from the side, and the calculation here, and then we can see the streamers link up and study the evolution of the features in the sun. I like these eruptions here, and prominence motion here, a couple of eruptions there, and our colleague Michael Zeiler just took a wide-angle view out on the ice. And this is similar to what Rob had in the movie, with the umbra here, and then you're seeing out of eclipse entirely there. You can see that the sun was below the height of these mountains. In the meantime, from where I was, we measured the temperature, and an hour and a half before totality, the day was warming up because it was morning, and it got all the way up to 8 degrees Fahrenheit. And then the eclipse started and went all the way down to -6 degrees Fahrenheit very abruptly. There's some thermal lag in the atmosphere, so the minimum was a little bit after the middle of totality, and then it warmed up and resumed what it would be doing that day. Here's the same thing in Celsius, where it was -13. It warmed up to -13, and then it went down to -22 in the course of the eclipse. So we're also now following the effect on the Earth's atmosphere, and not just what we see on the sun. And here's a group, and Rob and Helen are here, for example, with the support from the Committee for Research and Exploration of the National Geographic Society, and some extra support from Williams College for this event. And our colleague Terry Cuttle took this beautiful view from another side of totality. So I hope you can all come to the States in August 21st to see this eclipse that will cross the whole continental United States from west to east. And then many people will have iPhones, and iPhones can make surprisingly good images. Let's see if I can make this movie play. Maybe not. Well, in any case, you can see the structure of the here. So here's about a 30-second movie made with an iPhone, and there'll be millions of people doing this at the total eclipse. And I'm working with a group from the University of California at Berkeley, the Space Sciences Lab, that is arranged to receive all kinds of movies like this from all over the United States, all over the path of totality. And we're putting together what we call a mega movie with the help of Google to collect all the observations, and then people with more professional cameras and bigger telephotos will make what we call a terror movie and try to see the changes in the eclipse all across the United States. My colleague Glenn Schneider with his friend Jeff Sims, we're in a high-flying airplane, and this is just to show you a series showing the Umbra travel across the Earth on that occasion. Anyway, it is interesting to see these partial eclipses, annular eclipses, not just total eclipses. September 13th, 2015, there was an eclipse that was maximum in Antarctica, but it did reach Africa, and I wanted to be as far south as possible to get the maximum possible coverage in Africa, and we were able to see from Lago Haas, the point where the Indian and Atlantic Oceans meet, to see this partial eclipse through some clouds. And of course in space there aren't clouds, and they were able to see something of this eclipse. The moon was not big enough to cover the sun, but you can see it from where that spacecraft was and went across centrally. Now the last total solar eclipse visible from Earth was on March 9th last year, and went across Indonesia, several islands, and then out to the Pacific, where it reached only one atoll, and the partial phases reached Southeast Asia and Northwest Australia. And so here is the path over Indonesia. The equator is about there. But the weather statistics were not very favorable. Purple is bad for cloudiness statistics, and you see all the islands of Indonesia were not favorable. It was a little better in some of the straits. We went to this island of Ternate. Xavier, who was sitting by the exit there, went a little further up to Halmahera. I believe that was Halmahera there. And here is a simulation made by the simulation team, Science Visualization Studio at NASA's Goddard Space Flight Center. So the moon is projecting its shadow, or the sun is projecting the shadow of the moon onto the Earth, and it went across here, Sumatra, and here's where we got it. Here, and Xavier got it there, and went out into the Pacific. And here's another view, zooming in and showing you the locations in Indonesia where these simulations are showing the partial phases first, and then with curvature rounding out the dark part of the shadow, the umbra, going across the Indonesian islands and out into the Pacific, where it hit this little atoll there.
Yes.
Yes.
I was there.
You were there.
Well,
In the Pacific.
Yeah.
Good for you. Come tell me more about it later. So we were here. My group was here in Ternate, and at that point, the sunspot cycle had declined by a factor of about 2 on the average. And we could view everything, but through a generally cloudy sky, and some people 2 kilometers away had a better hole than we had, and some people not that far away had a worse cloudy sky than we had, so it was pretty spotty at that time. It was still better than the overall statistics, and we were glad to have seen the phenomenon. And I stress again that this is with filters for the partial phases, and these are without filters for the totality. So here's a different camera view with my Nikon wide-angle view. We were looking over the ocean here, and we had a reasonable hole, but some people who just went a kilometer or two away just had a bigger hole, and that's what happens. So here's a series of images, and again, the different exposures, and we put these together to make a composite. There was a beautiful prominence, huge prominence on the edge of the sun on this occasion, and here's this composite here. Now, people have asked me about what you can do from Earth. So on the top of Mauna Loa in Hawaii, at about 4,000 meters of altitude, they have a coronagraph now from the High Altitude Observatory, as it's called, that can block out the sun and a little bit above that, and then make some measurements above that. You can see the detail is nowhere near as good as we get an actual eclipse, but they can see some streamers. This is just an effect on the dust there, and follow this. So this is the new upgraded coronagraph they have in Hawaii, and they can process that image and give you some idea of the inner corona, but by no means as far out as is blocked by the space coronagraph. But this is the best that imaging on the surface of the Earth can do, even at a mountain at 4,000 meters of altitude. I did ask somebody to measure the temperature every 5 minutes or so, as we went through totality and before, and you see that the day was warmer. It's here we are. It's 26 degrees, and this is not Svalbard anymore. This is Indonesia on the equator, and it got warmer and warmer. But then, as the eclipse began, it leveled off, and then it dipped from, and it might have gone up to 30 or so, and instead it went down to 28. It was humid, so each effect is different. But then I did notice there was one point missing. I just put a red dot there to show where that point is missing, right at totality, and I went back and looked at the original notes that my colleague had made, and it said, too dark to read the thermometer. Anyway, so here is the spacecraft view, and you can see now there are very few streamers and more equatorial ones, and the spacecraft image shows some beautiful structure on the limb that was covered over by the moon. But you saw the spacecraft just barely went by, so it actually had 4 minor partial eclipses and no totality from where that spacecraft was orbiting. So they can't control the orbit, but they are alert when there is an eclipse. And in fact, there was a Japanese spacecraft called Yoko in which they missed turning off the guidance system at an eclipse, and the spacecraft went spinning out of control, and they actually lost that spacecraft as a result of the eclipse. One of very few negative results of an eclipse that I've ever heard of. So anyway, here's the swap view of those eclipses, and we do get these beautiful high-resolution images. There's the fourth one. And then there's an X-ray satellite that the Japanese have, an X-ray camera built by Leon Golub of the Harvard-Smithsonian Center for Astrophysics, and that's even hotter gas. So this is closer to 15 million degree gas, not just the 1 million degree gas. And you see only some very hot spots on the surface above the active regions. But they did get a total eclipse there. You can see some X-rays on the solar limb. And so this is on the Japanese Hinode spacecraft with the XRT, the X-ray telescope there. So, but this is a real phenomenon. You can really see, play that again, the meteorological satellite really just shows you the umbra going across the Earth, and the people on the space station can look down and see that, and the weather satellites can see that. And September 1st, 2016, there was an annular eclipse, which is, of course, the kind we're most interested in here now, that went across Africa, the peak over here in Tanzania, and went across Madagascar at that point, and you see the broad range of the partial eclipse. And I was wondering about going to Tanzania, but we had a very long bus ride in Indonesia, and we didn't really want to take the long bus ride from Dar to the eclipse path here, and we're able to fly in over here to a French island called Réunion, part of France, and we saw a number of our friends there, and then Xavier makes these wonderful maps, and he has his own website, but I remember, I always go through my website, which is just eclipses.info. So all you have to do is remember eclipses.info. And then you can click on Xavier's map, and then you can zoom in. And if you click on any given location, it gives you the times and the amounts of totality and other features about that. This was the information for Reunion Island. So the weather was clear, and we got a nice view of annularity. So this is just a GIF putting that together. And so I hope we all get images with which we can do this on Sunday. And my alumnus, Mujo Lu, put together some composites just showing, I was taking images every 5 minutes, and then more often during annularity, and we could see all these effects. That was just a lot of fun to see, and I hope we get the ability to do that again this year. The people there loved it, and I'm sure the people around here will love what we see on Sunday too. Now, of course, for eye protection, you can't look at the annular eclipse at any time, even when there's only a fraction of a % of the sun left. It's just too bright to stare at. But we do have all these different eclipse filters of various kinds. So these are the glasses. These are two of my grandchildren wearing the glasses. They're available very inexpensively. Do we have glasses for everybody here? I have some with me too. And I prefer these actual cards because you only have to put them up for a while. You don't want to wear the glasses all the time anyway. Things change very slowly for an hour and a half for the partial phases. And then it is possible for a class to get a big piece of filter, and we want to encourage the students to go out and enjoy the eclipse, and the teachers may prefer having the class view in this way. And then you can make pinhole camera images, and you can make a hole in a piece of cardboard, and I use a cheese grater because I have 100 holes ready, and just get a lot of partial eclipse images there. Here's the class out in, this is the age 3 class out in Pasadena, California for that eclipse. And but we do have trouble. Here's my alumna, Christian Shapiro, with something from Australia. This is some years back, but eclipse glasses can hurt your eyes, and that's wrong if they're properly made and properly certified. So some people, Terry Cuttle, who I showed before, some people now in the United States have worked very hard to get certification from the International Standards Organization, and there is an ISO number. Some of you may know on your cameras you now do the speed with ISO. So the International Standards Organization has approved a certain set of qualities that these eclipse glasses must have, and then they are not, in fact, harmful. And so we've been trying to get out in advance of that in the United States and work with the Ophthalmological Association, the medical associations, and try to keep people from giving these false warnings. So anyway, here's what we're going to have this summer. The partial phases will extend to the middle of South America and go up through the Arctic, Alaska, Hawaii, even to some of Siberia, some of West Africa there, but the path in totality will go across the middle of the continental United States for about an hour and a half, and then 90, 80, 70% off to the side. So all of the United States will, to the south here, will have at least 70% and 85%, or at least 80 in Florida. But as I said, 99% means that there's 10,000 times more light. And we're working to try to educate the American public and to try to get as many people in the zone of totality. Jay Anderson, a meteorologist, has long made a hobby of doing cloudiness statistics based on satellite imaging. So red is cloudy 100% of the time. Blue is different stages, but blue is better. And so that's why I have chosen to go with my group to the northwest United States. And of course, statistics are not the actual circumstances on eclipse day, but I'm going to observe from over there. Now, the National Oceanic and Atmospheric Administration of the United States has just launched the first in a series of 3 satellites known as GOES-R, and there's going to be S and T to spare. This is a $12 billion project. It's a huge project for weather reconnaissance. It's operating now in a test mode, taking fantastic pictures with better resolution of the surface of the Earth and at a faster cadence than ever before. But some bright person a few years ago realized that if the cameras are pointing down, the solar panels are pointing at the sun. So for the last few years, they've put a solar telescope right adjacent to the solar panels for continual monitoring of the sun. And with this new spacecraft, then we think this guarantees another 20 years of spacecraft observations of the sun. This GOES 16, as it's now called, in the Solar Ultraviolet Imager, SUVI, and Dan Seaton has gone there to Boulder, Colorado to work it, and it has these 6 different filters. These are all in the ultraviolet. A red light for your eye is around 6,000 angstroms, so this is a 20th the wavelength of red light. So this is very short wavelengths, and this is a cooler gas, and these are hotter gas. And here are the temperatures in a logarithmic scale. So this is under 100,000 degrees here for this helium image, and then almost 1 million for this iron image, and then over 1 million, and then there are some flares that enable you to see 10 million or above. And so that imaging they're still being tested. Nothing's been released yet, but I understand it works. It has a bigger field of view, FOV, than the preceding spacecraft, and bigger than the Solar Dynamics Observatory. So we can see these streamers out a little bit into space with processing, and that's all being tested now and should be ready for the eclipse this summer. The sunspot number has been precipitously dropping off. This is the latest publication as of the 1st of February. So there are very few sunspots on the sun. Here's again the February 1st showing the double peak and then the strong decline. And this is today's sun from different venues. The so-called Global Oscillation Network Group is a network of ground-based spacecraft, and here's the magnetic ground-based observatories, and here are the very few magnetic regions there, and then just these very few sunspots that show, and then H-alpha of the chromosphere just shows minor brightening, and when you go up to the million-degree gas, then you just see it's pretty calm, a little bit in a couple of active regions. There are these big, what are called coronal holes, where the corona is relatively less dense, and you see in the high temperature X-ray telescope very, very little, just a little bit of emission from that one active region. And so Michael Zeiler, a map maker, professional map maker, has been using his skills on eclipses for a few years, and this is his GreatAmericanEclipse.com video of the path across the United States and showing all the various cities that it will go through. It's going to just miss St. Louis, go into Tennessee, a little bit of North Carolina, and wind up in South Carolina, but I've already shown you the cloudiness statistics, and which are overall more favorable to the west than they are there. So here is the NASA simulation from Ernie Wright, showing the sun projecting the path of the moon onto the Earth. And now we see the partial phases hitting the American continent, and there's Salem, Oregon, which is where I'm going to be, there as the path passes through Boise, Idaho, close to there, Casper, Wyoming, a little south of Omaha, Nebraska, a little north of Kansas City, a little south of St. Louis. It includes a bit of Nashville, and winds up with a little bit of Charleston, South Carolina. We're going to have a meeting in South Carolina of the task force of the American Astronomical Society. There are a lot of problems. I was telling Nestor before, when we were driving on this empty road from the airport to here, that in little isolated roads like that, the transportation people are expecting 60,000 cars on Eclipse Day. And so there are a lot of problems with facilities and food and sanitary facilities and watching out for traffic jams on Eclipse Day. I mentioned the Mega Movie Project that I'm affiliated with will gather images of the eclipse from over 1,000 volunteer photographers and then people from members of the general public and make this expanded continuous view. We do want to get a lot of the Bailey's beads. Here's a series that Fred Espenak took. He's coming along, I guess his name is covered there, but he's coming along with our touring, I believe, to the eclipse. Now he's just coming off with the Antarctic cruise, so we're going to make some measurements of the edge of the sun. And then a big grant was just announced by the National Science Foundation for Matt Penn and others for Citizen Cape, the Citizen Continental America Telescopic Eclipse Experiment. They're having almost 60 telescopes, identical telescopes, across the 3,000 miles of the United States, again, to make a movie and to measure all kinds of details and study the dynamics in that inner 2.5 solar radii of the corona. And then my colleague Shadia Habal from the University of Hawaii is a major solar physicist doing experiments, and she wants to study in particular how the excitation of the corona changes from radiative to collisional, and she has a number of high-resolution observations she'll be looking into, comparing with past observations, and so here's some of her past events. And then this is iron 11, 10 times ionized iron, and the green is 13 times ionized iron from the 2008 eclipse, and she's studying some of the features that she sees erupting there and measuring velocities in them. So I'm just finishing up. Some students of mine and I made an 8-minute movie that's available on the web free. It's called Colors and Motions of the Sun. solar-center.stanford.edu, and then you can just click on various things or go to CMOS for Colors and Motions of the Sun, and you can show that to your family or students or anybody. And there is something about space observations, there is something about eclipse observations there. And then there are other eclipses that then come in the United States. We'll have one in 2024 that goes through the eastern United States. In the meantime, there are lots of activities you can do. My students just in snacks one day made some solar eclipse cupcakes here, the partial phases, and then we had totality with prominences there, and then the sun just in the red H alpha radiation, and then solar minimum with a few sunspots, and solar maximum with a lot of sunspots, and eruptions of prominences. I don't know if you have candy corn in Argentina, but it looks reddish, and they've used it. And then a coronal Messi ejection, a coronal mass ejection. So these are very inventive students. And then this is what's pertinent to this weekend with the annular eclipse cupcakes. And we've also been observing transits of Venus and of Mercury, so we're proud of them. Fred Espenak has given me permission in the English edition of my field guide, the Spanish people updated it by themselves, to have the next few years of eclipses here. And so in 2019 there'll be a partial in January, but then in July an eclipse across the Pacific that winds up on July 2nd in Chile, over to the boundary with Argentina, there. And then I guess I don't have the graph for 2020, and then there's one that goes more, you probably all know this, goes more centrally here. So here are these images here. So 2019, just at the very end, reaches Chile and Argentina, and then 2020, further south, goes, so that's closer to where we are now on December 14th, 2020. You can see these in Michael Zeiler's set of all these Eclipse maps. Here's color motion of the sun again. And then in closing, I just wanted to say that I've been using my Eclipse equipment also to study, especially Pluto. When Pluto goes in front of a star, the same fast readout CCDs we use for studying the heating of the corona at eclipses. If you take the filters away, we can watch the light from a star filter through the atmosphere of Pluto, and we've been monitoring Pluto's atmosphere. And you all know that in July 2014, the New Horizons spacecraft from NASA went right by Pluto. This is an image taken a little before to show Pluto and Charon. Well, they always knew that the spacecraft, once it passed Pluto, was still working. So what can they do with it? Well, they can't change where it's going, but they can look in advance of its path to see where it might be going near. And they were sure that in the 10 years it was traveling, some objects would turn up in that path, but nothing did. And they finally managed to get 100 hours of Hubble Space Telescope time, which, as you can imagine, is not easy to get, to find some objects. And they found this object, and a couple of others, just a little faint object moving. It's probably only 30 kilometers across or so, and it's called 2014 MU69. It was discovered in 2014. So here's our path here for Sunday, but on July 17th, it's going to go almost in the same path here. And if we can figure out more precisely where it is by just its projection on the Earth, improving on this model, they are willing to retarget the spacecraft, to go very up close to this object, even closer than it went to Pluto. So this is big stuff. But what we need is to figure out where it is. So we may have to put, if the object's only 20 kilometers across, its shadow on the Earth is 20 kilometers across. So it means we need telescopes every 15 miles for, we're a little uncertain where it is, so for 100 or 200 miles, we need telescopes every 15 miles. And these have to, the star is not that bright, maybe 15th magnitude, so we need 35 centimeter or larger telescopes, 14-inch or larger telescopes. So if any of you have telescopes in where you are and willing to bring them to somewhere in Chile or Argentina for these events, come see me about that. And because we're trying to work on that, and NASA and the June 3rd event, if we get that first, that NASA is willing to fly at Sophia aircraft to try to get the July event and really pin things down. So we're working on that and planning on that, and it's an exciting thing. And it's quite noticeable that this path is really quite similar to this path. So maybe there are people in this room who want to cooperate, be able to cooperate with us on those observations. So that's what I have to say in my, I guess, closing talk of this symposium. And I wish you luck, and I look forward to traveling with you, especially on Sunday, to Facundo or thereabouts to see the annular eclipse of the sun. And I'm glad to talk to you before and after that about photography or what to do with all the images we get. And at the moment, I'm very glad to answer questions.
¿Cuánto calcula que baja la luz? Digamos, si me puede decir. sea, nunca vi uno. Vi la imagen que había del Polo Norte y bajaba bastante.
Which
Pero no sé.
quantity do you estimate that the light of the sun goes down?
To the
The
simple eye.
quantity, well, I don't estimate that the light of the sun goes down. I go to eclipses.info and I click on Xavier Jubier's map, and in the upper right-hand corner it says the percentage that's covered, which I believe is 99.3, and on the left side it gives the area that's covered, which I don't remember. Do you remember what it is?
Percentage of surface is obscuration, so it's on the left, and on the right it's the magnitude. So it's not the surface, it's just the by diameter.
So do you remember what the number is, Xavier, for the obscuration?
In the lab it should be 99.998. Yes.
So it's pretty...
So the light will be much lesser.
Yes, it will be a very special light. But you see the eclipse, for example, in 2013 that Jay showed in Gabon. This was total, but it was only 1.001, I think. So you see a very small difference. It's a big difference because it's night and day. See? Yes. Yeah, you have to really be, even 0.9999 is not enough.
And there are some people, Freddie Durst from Germany is really overexposing an image, and sometimes he can see a tiny little bit of front if you like that.
To the earth, you will see. I'm not intended to photograph the event, but the people. Okay. If I'm watching the people, I will see.
Yes, so if anybody who's going to watch the people, or anybody who's going to use a camera, let us first of all make a plea to turn off your flash, because it's just disturbing. But the flash goes on automatically in many cameras, and there's a remedy for that too. It's called black tape. So put some tape over the flash in your camera, lest it start automatically. Second, when people use cameras to look at an eclipse, the eclipse is usually pretty small in the sky, and if the autofocus is on, it sometimes tries to find the autofocus. If you know what hunting is, you do. It hunts back and forth, and you can use the whole eclipse, never being able to take a single photograph because your camera has not automatically found any focus. So you want to turn off autofocus and focus manually. And now, and then if you're at a totality, you want to take that filter off at totality without changing the focus. But for the annular eclipse here, you will have been focused in advance. There can be some changes in focus over the hour and a half, or longer, 3 hours, just from the cooling of the atmosphere. So there can be some changes in the camera that change the focus. So you should focus periodically. But you do want to focus manually, and you want to cover your flash with tape.
Tienen todos de que estuvo hablando, ¿no? Para sacar las fotografías, porque está preguntando si va a poder fotografiar a la gente en realidad.
Yo en realidad voy a apuntar a la gente y para tener una idea de la variación de la luz, como nunca lo vi, pero por lo que dicen va a ser mucha.
Sí, la caída está.
At the beginning there is nearly no variation, then it's quite steep. Okay, so 5 minutes before, 5 minutes after, in that time frame, the change is quite, big.
Yes. Also, you don't really know when you're outside tomorrow and you see your shadow. The edge of your shadow is a little fuzzy because after all it's being cast by something that's a half a degree across. But when you get just a crescent, that's a fraction of that, say a tenth of that, you can't necessarily know what's wrong, but you know something's wrong. The shadow looks eerie. The light from the outer part of the sun is a little different, and so you get a feeling that something strange is going on, and the shadows look strangely sharp.
The shadow is sharp.
Yes, and so these are, yes.
Mónica.
Sí. En una de las conferencias mostró una diferencia de temperatura de 7 grados. ¿Puede hablar?
Yes.
With a difference in temperature of 7 degrees.
7 degrees.
Well, it was much greater in the Arctic where it was very cold, and much less when it was humid in Indonesia. And we're probably in between there. So I do expect a few degrees. So please, when you see me, remind me that I have some automatic temperature measuring buttons in my camera bag that I have, and that we'd like to have the day before and the day after, but the comparison, but we're not going to be able to do it this time. But please, everybody, remind me to take those out as soon as we get to the site, and we'll get some automatic measurements. And if anybody wants to, I have a couple of thermometers with me too. If anybody wants to make those recordings, the temperature people don't really like. You have to shield things and be careful in various ways that we astronomers are not used to for ground-based temperature measurements. But actually, my most recent published paper was in the Philosophical Transactions of the Royal Society in September, because it had a special issue on the effect of the partial eclipse on the weather on Earth in England from that 2015 Svalbard eclipse. And when I heard about it, I wrote the editor and said, "Gee, you've got all these partial eclipses. I have total eclipse from Svalbard. Can we get that in?" And past deadline, we managed to add that article. But there are about 15 articles on various aspects of the effects on the Earth's atmosphere of the eclipse, even at a partial eclipse that was not even as broad, as deep as what we're going to have here on Sunday. So there will be profound effects on the weather.
Yes.
I'd like to point out something else that's unusual about this annular eclipse. Namely,
Daniel, do you want to get the microphone?
I think I'm loud enough. I wanted to point out something special about this annular eclipse, because the ring is extremely thin, much thinner than during any other annular eclipse, I think, in the last 18 years. And what I remember from its Saros predecessor, the one that was very similar in Australia in 1999, was that you could see planets during annularity, because the sky gets much darker than typically during an annular eclipse. So to observe this and look for planets, you cover the sun, the annularly eclipsed sun, with your hand, because you cannot look there directly. And then look to the left and to the right.
With the thumb.
With the thumb. The thumb is enough.
Big enough. If you just hold the thumb in
Yes, one eye.
big enough.
Yeah, your thumb is about 4 times bigger across than the sun, actually. So you can easily cover the sun with your thumb.
So look around if you can see. I'm not sure. Can you see?
But as most of you know, Venus has been especially bright, tens of degrees away from the sun. So we certainly should be able to see Venus off to the to the east, because it's after sunset. It's been high in the sky, so we certainly should be able to see Venus very easily, and Mars has not been that far from there, so it will be worthwhile to look for planets in the sky.
Si ocultan el sol con el dedo, es posible ver los planetas. Ese es el tema. Pero yo no sé si vamos a tener tiempo como para ver los planetas, ocultar el sol. Este es un eclipse un poco breve, así que disfruten el eclipse y el 19.
Actually, in my field guide too, there's a graph showing how far the planets are from the sun, so we can check that right now.
Okay. Sí, se va a chequear. ¿Alguna otra pregunta?
Jay should point out that this recent edition of his book is printed in Spanish. Earlier today, somebody said, why was the publication printed in Spanish? But
Oh, okay. So there are really about a dozen years ago, this Madrid publishing house put out a Spanish edition of my book, and I worked with them on the translation. We gave them all the pictures and all that. And then for this eclipse, we did a major update of the 14th printing of the English edition, and we offered it to the Spanish, and we discovered that they had hired a distinguished Spanish astronomer to do his own updating. So they've diverged a little bit, and he doesn't have the most extensive eclipse coverage, but I read what he did, and it's quite good. So there is now this new edition that's just come out a few months ago of the Guia del Campo de las Estrellas y Planetas, and maybe Beatrice can send out the instructions as to the name of the publisher and how to contact.
Yes, of course.
afterward. And then if you want the English edition too, that's available. I have a website at solacorona.com that lists all these different books with links. And I guess I should add the Spanish one too.
No, it's okay. Thank you. I have my
Well, thank you very much, everybody. Thank you for giving me a chance to talk about it.